Hi folks, it's Alan here and I'm back in my electronics cave continuing to develop this thing, which is my supercapacitor based power supply. Now if you've seen my previous video, you know that the power supply is designed to use two of these, a bank of supercapacitors. Essentially what it's doing is it's permanently connected to the mains, but actually the output source is never connected to the mains at all. It's only ever powered by these supercapacitors. So with two banks, one bank is permanently charging and the other bank is permanently discharging and supplying the load. And that gives me fantastic electromagnetic interference rejection, both noise coming in from the mains but also noise going out from the equipment onto the mains. However, there are some interesting challenges with this because I need to switch over from bank A to bank B on a fairly regular basis. This has required some fairly clever design on the output circuitry. And the first thing you may be able to see here is this large beast here, which is another output capacitor. And essentially, during the few milliseconds it takes me to switch from one bank of supercapacitors to the other, this is the capacitor that's going to be holding the output charge. And this is a circuit that's designed to see exactly what happens and to permanently keep that output capacitor charged, but also allowing a small amount of voltage drop. So basically, whenever I push this little tiny button here, what that will do is that will basically disconnect the load from, disconnect the input power supply from these two regulators, and I'll start to see the voltage on this capacitor here drop slightly. And what I'm trying to do here is measure exactly how far that voltage drops, and therefore exactly how much time I've got between one bank of capacitors being disconnected and the next one being reconnected. So what I'm going to do is switch on my power supply. That's my supply switched on, and you can see now I'm getting about 16 volts output on this, and that's basically the voltage across that large capacitor there. If I push trigger on my oscilloscope, you should see, yeah, you can also see exactly the same thing there. Basically, you can see that the oscilloscope is measuring 16 volts, and this is set up so that it triggers if the voltage drops below about 15.5 volts. So what will now happen is that once I've set up and added a load to this, I'm going to push this button here very, very briefly, and that will disconnect the output supply, or the supply from that output capacitor. And what I'll be able to see is exactly how far that supply drops in the very brief period. But first thing I'm going to do is connect up a fairly sizable load. So I'm going to connect these two resistors here. And this gives me a decent chunk of current flowing through that. So I've got about 1.8 amps flowing through this. And now what I'm going to do is push this button for a brief period of time and see what appears on the oscilloscope. And there we go. That's a perfect trace example of exactly what I was expecting to happen. And what you can see here is that when I push that button, the voltage from that output capacitor starts to sag immediately, and it takes a few fractions of a second. This is currently running on a 25 millisecond time base. So you can see here that within the first kind of 25 milliseconds there, I'm losing about 4 or 5 volts of that voltage across that capacitor. So I've probably got about 5 milliseconds to switch over, which is actually ample. So I'm really looking forward to seeing what I can do with this. And I should also mention that the final output of this won't be coming straight from that capacitor. There will be another stage of regulation designed to make sure that the output voltage is absolutely fixed. Looking forward to seeing what this does.